Hello class, it's Mr. McAllen again, BC guys, and I just wanted to go through another question with you. It's on a Taylor series that, as you can see here, they give us the Taylor series. I'll give you a moment to just read through the question, and I'll just pause the video so you can read it, and then we'll get into solving it. So let me just pause the video for a moment. Okay, so hopefully you've had a chance to read over the question. And the first thing they want us to do in part A is they want us to find the interval of convergence of the power series. So what we need to do is we're going to consider absolute convergence first with a ratio test. And this test is basically by looking at the limit as n goes to infinity of a to the n plus 1 over a to the n. And we will have to set that ratio with the general term. So we'll have, remember when we take the absolute value of the entire ratio, we're not gonna have to worry about the -1 term. So we're just have n plus 1 times x to the n plus 1 over n plus 2 times the reciprocal of what a to the n would be. So we're going to have n x to the n, the reciprocal I said, so I should do the reciprocal, n plus 1 over n x to the n. Remember, this is the absolute value. We're not concerned about signs. And we'll find the interval of convergence from this. So I like to collect terms, and I made a little mistake here because actually no, we're fine. I just have to make sure I write my n's better. So I'm going to have n plus 1 times n plus 1 over n plus 2 times n, and in the other fraction I'm going to just have x to the n plus 1 over x to the n. And when I limit n to go to infinity, I'm going to just identify for this portion here that when n goes to infinity on that part, that term is going to be n squared plus 2n plus 1 all over n squared plus 2n. And for this part here, this is going to simplify where I'm going to end up having just x to the n times x all over x to the n. And this will cancel. And now I'll just be doing limit as n goes to infinity. And this x will come outside of the limit. And using L'Hopital's rule, or just thinking about the end behavior of this function, we know that this limit here goes to 1 times x. And in order for the ratio test to declare convergence, this has got to be less than 1. So what we find from this is the absolute value of x must be less than 1, which tells us that our radius of convergence is from -1 to 1, and now we have to go and check the endpoints. So let's do that. Okay, so I'm going to zoom out a bit so I can see the original problem again, or the general term, because what I have to do now is I have to plug the endpoints into this general term. So so I'm going to just write it over here, -1 to the n x to the n over n plus 1. And I'm going to plug in my left endpoint and evaluate that. So when I plug in my left endpoint, x equals -1, I'm going to have -1 to the n times n, and this can be -1 to the n power all over n plus 1. And I'm going to sum that up from, as the series says, from I'm going to go from 1 to infinity but I'm going to start writing out the terms and see what I see develop. So here again, -1 times -1 to the both to the n power becomes -1 to the 2n, and I have n over n plus 1. So when I write out this series, I'm going to get 1 over 2 plus 2 over 3 plus 3 over 4. And as you can see from this series, that this is going to diverge. Now you may be wondering, well, what's happened to the -1? But since it's raised to an even power always, the sign won't switch. In fact, that -1 won't even be seen in this series. It's just going to be, every term will be positive, and if you let this term continue on, it just diverges and goes off to infinity. So in the next one, I'm going to use the same. I'm going to now apply the point x equals +1. So I'm going to have, when I plug in +1, I'm going to have -1 to the n power n. I'm going to have 1 to the n, which is just going to be 1, all over n plus 1. So when I write that out, I'm going to have for my first term -1/2. And then my next term will be positive. Oh, let me just go see what the n value would be. N starts at 1, so it's going to be -1/2, and then it's going to be +2/3, and then -1/4, and then positive. And then positive 4/5, and so on. Sorry, I had technical difficulty there for a moment when the windows popped up, so I think we're back in order here. So now what we have is we have an alternating series. But I don't believe it's a alternating harmonic series, because when we check the nth term, you see that the limit of n over n plus 1 as n goes to infinity, that has to go to 0 if this is going to converge. Just the fact that the signs are switching from positive to negative isn't enough. You have to show that the nth term, or the when the series gets out to, or the general term, when it gets out to an infinite value, that it approaches 0, and this does not. This approaches instead 1. So as a result, this will not converge. So our interval of convergence is going to simply be from -1 to 1 without the endpoints included. Okay, we're back again. And now in the next part, it asks us something more elementary, but it asks us to do it with